Okay, so let's go ahead and get started. Okay, so today's class is on how to do branching in assembly language, and being able to do branching in assembly language, it allows you to do, like if statements and case statements in assembly. Now, there's some things we need to review from CP 133 before we get to the branching. And then when we get to the branching, there's several examples I have, and I'll do one of the parts from software assignment number 2. Like I'll do the first part of it, or we'll do it as a class. And then after we go through these examples and I do part 1 of the first or the second software assignment, you should be able to do part 2 of software number 2. Okay, so at the end of lecture, and it's probably going to go for a little over an hour from where we're at right now. We may take a break at some point. We probably will take a break at some point. And then you'll have the rest of the class time to work on the assignments. Now, the priority should be to work on the program counter if you're not finished, because that's due tomorrow. And then this assignment, like any Thursday assignment, is due on Monday of next week. Okay? All right. But there's a few things from 133 we need to review from the start here. And the first is this, that in 133, it was talked about how you can multiply a binary number by a whole number power of 2. So, that's multiplying by 2 or 4 or 8 or 16. Okay, whole number power of 2. So, does anyone remember how to do that? Like, we started out with this binary number here. What's this in base 10? What is it? 6. Right, because remember, this is the ones column, 2, 4, 8. So this would be 6 in base 10. So if I want to multiply this by 2, how could I do it? Sure. Right, shift it what direction? Left. Right. See, we take this binary number, we shift this one over here, and this one over here, and this 0 here, and then bring in a 0. Okay, so the vacated spot is filled with 0. Well, now we have a 12 in mind, right? And if I were to shift another place to the left, right? If I were to shift all this over one more place to the left and put in a 0, that would be 24. And do it another time, that's 48.
So when the ones go up to the left side, do they go back onto the right side, or does it get added with zeros?
No, in order for this to work, what comes in, what we call the vacant bit, it's got to be a 0.
Oh, right.
Yeah, otherwise it wouldn't work.
It'd be an odd number.
Correct. Okay, so that's how we would multiply by a whole number power of 2. It's just shifting the appropriate number of bits to the left. Okay. How about if I want to divide by a whole number power of 2? Shift right. Okay, just go the other way, shift right. So here, this is 8 in base 10. So if I shifted one place to the right, this 1 comes over here, this 0 comes over here, this 0 comes over here, and then again, the vacant bit is 0. Well, I just went from 8 to 4. Right? If I want another place, I have 2. If I want another place, I have 1. So you want to divide by a whole number power of 2. You just shift the appropriate number of bits to the right. Okay, you'll see that you'll need these for the part of software number 2 that you're going to do. Okay, so any questions on this here? Everybody remember this? This is talking about 133, right? I talk about it in my class. I would assume other instructors talk about it. Okay, how about this? What if you had, just a bunch of different binary numbers, and you wanted to look at those binary numbers, you wanted to look at the bits, and from those bits, determine whether you have an even binary number. Like, what would be the easiest way to do that? Yeah, exactly, right? Because the least significant bit is the ones column, right? So if that bit was a 0, because all the other columns are fractions of 2, right? No matter what these bits are equal to, if this least significant bit, which is the ones column, is a 0, that would be even. Right? If it was a 1, that would be odd. Okay, everybody see that? All right, how about this? What if we had, some binary numbers, just random binary numbers, and just by looking at the bits, we wanted to determine whether we had binary numbers that was divisible by 4.
The two least significant places would have to be zeros.
Exactly, right? And one way you could determine that is if, you had to write something that, like, personally, for me to confirm that, what Grady said, I would have to write down the bits to make sure. So, let's take 4-bit binary numbers. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and I could keep going. So, I would look at this and now some people would say 0 is divisible by 4, some would. But 1 is not divisible by 4, 2 is not divisible by 4, 3 is not divisible by 4, 4 is divisible by 4, 5 is not divisible by 4, 6 isn't divisible by 4, 7 is not divisible by 4, but 8 is. 9 is not divisible by 4, 10 is not divisible by 4, 11 is not divisible by 4, but 12 is. So you see, by writing out these bits, you can pick a pattern up, right? That if you have a binary number that's divisible by 4, the last 2 bits are 0. Okay. Now the reason why, I wrote these out and I look for the pattern is because you're going to see in this class as we go along, there's going to be needs to do that. Okay, there's going to be needs to look at different binary numbers and different data and be able to pick out patterns. Okay, so I'll talk more about that later. This is just the first stage of, looking for a pattern. Okay. So any questions on anything up to this point? All right, the next thing is something called bit masking. And bit masking, depending on who your instructor is for 133, may have been talked about or may not have been talked about. But what was definitely covered in 133, no matter what instructor you had, is AND gates, right? Because in 133, you learn all about the basic logic gates, right? And or and more and all this, right? So who can tell me the truth table for this 2-input AND gate?
0 all down the board until A and B are 1.
Right. Yeah, in order to get a 1 out of an AND gate, all your inputs have to be 1. Now, this is a 2-input AND gate, so 2 inputs have to be 1 to get a 1 out. But if you had a 3-input AND gate, a 16-input AND gate, a 32-bit AND gate, it would be the same thing. Right? All the inputs would have to be 1 to get a 1 out. If at least one input is a 0, the AND gate's going to have a 0 output. Okay, but as Landon, right?
Yeah.
And as Landon said, the truth table would look like. Only get a 1 out when both inputs are 1. So everybody remember the AND gate? All right, well, bit masking is a method where you can keep, like say you have, a bunch of binary bits. Well, bit masking is a method where you can keep the bits of interest and make all the other bits equal to 0. Okay. So, for example, let's say we had this binary, well, it's represented in text. Okay, here's a text, string, if you will. And as you know, X is not a character in text. What I'm representing here with an X is I'm representing any hex character. So this X here could be any hex character 0 through F, right? This hex character could be any character 0 through F and so on. Okay, wherever you see an X, just think, oh, it could be a 0 or a 0 through F. Now, we've talked about this a couple of times in this class already, and that's how many binary bits are represented by one hex character. 4, exactly. So, you know, this hex character represents 4 bits, right? 4 bits here, 4 bits here. So there's 8 hex characters. So therefore, there's how many bits? 32 bits, exactly. Okay. So just think of this as being 32 bits. And let's say that for whatever reason, I'm only interested in the last 2 bits. Like I don't care about the other 30 bits. I'm only interested in the last 2 bits. Okay? Well, what I can do is I can take this and AND it with the following. Okay, so I wrote 7 zeros here. So just think, you know, and this again is in hex. So this is like 4 zeros, 4 zeros, 4 zeros, 4 zeros, 4 zeros, 4 zeros, 4 zeros. So this is 28 bits, right? So these 28 zeros are going to be ANDed with the first 28 bits of this number here. That can be anything represented by a hex of 0 through F, which is 4 zeros all the way up to 4 ones. Well, if I AND, you know, just think of this X now as being a bit. Well, actually, let me use a different symbol. I'll use B. B per bit. If I take any bit and I AND it with 0, I'm going to get what? 0, right? Because it doesn't matter whether that bit is a 0 or 1. If I AND a 0 or a 1 with a 0, it's going to result in a 0, right? Because I need 2 ones to get a 1, right? So this is going to be. So you see, by ANDing these 28 bits that are equal to 0 with these 28 bits, well, that's going to make all those 28 bits equal to 0. But if I take a bit and I AND it with 1, what am I going to get? The bit, right? Because this bit could either be 0, 1. So if it's a 0, I'll get 0 out. If it's a 1, I'll get 1 out. So you see, if I take a bit and I AND it with 1, I get the bit. So if I get this 32-bit binary number, and I only want the last 2 bits, I AND all the bits with 0 except for the last 2 bits, right? The last 2 bits, I make a 1. So how would I show that in hex? Like, what would that hex character be if I'm only going to let the last 2 bits of this be a 1? 3, right? Because a 3 is 0, 0, 1, 1 in binary. So you see, this would make 30 bits equal to 0 and just keep the last 2 bits, whatever they are. Okay? How about if I was only interested in finding out whether this 32-bit binary number was even or odd? What would I AND it with? What would this be? 1, right? Because I'd only want the least significant bit, right? So if I want to mask this where I just want to see what the least significant bit is, right? I don't care about the other 31 bits. I would AND it with a 1. Okay? Any questions on that? All right, because all of this that we talked about, the power to multiplication, power to division, you know, even odd, looking at the least significant bit, divisible by 4, looking at last 2 bits, that's going to come into play for your assignment. Okay, software 2, part 2. All right, so any questions about anything up to this point? Okay, so now, that was basically review from 133. Now we're gonna talk about branching in assembly. So this is, new CP 233 stuff. So the first thing is, and I mentioned this at the very beginning, branching allows you to do if and case statements in assembly. Now, every bench has this handout. It shows a listing of the instructions. This is just a brief listing. Again, pages 18 through 50 of the assembler language manual has all the detailed descriptions for each of the instructions. But on that listing that you have, how many branch instructions are there? Approximately. The branch instructions start with a B. Yeah, there's at least a dozen, right? It's probably a little bit more than a dozen. Well, even though there's, 15, 16, whatever the number is of branch instructions, only 6 are real instructions. You remember, this goes back to the first day of class. We talked about how there's real instructions and there's pseudo instructions. Okay, what's the difference between the two? What do we mean by real?
It doesn't contain other instructions. It's like a base level instruction, it's not.
Okay, I like the word base, yeah, and more specifically, what base would mean in this case is that the real instructions are the instructions that the microprocessor actually executes. Okay, pseudo instructions are for readability and convenience. Sometimes pseudo instructions are still a single real instruction with like a special value. And then other times, pseudo instructions can be multiple real instructions. So for example, if you look at the assembly language manual, right, where all the instructions are and all the detailed descriptions for each of the instructions are at. Well, if you look at, let's see, we can find one here somewhere. There's an instruction, a branch instruction, BNEZ. Okay, it stands for branch if not equal to 0. And if you read the description, in the description it says, it's a pseudo instruction based on the branch if not equal instruction and is equivalent to a branch not equal with a certain register 0 or register X0 that we call register 0, right? That's one of the specialty registers that's in the reg file. Do you remember why that's a specialty register? Like what's special about register X0? We haven't talked much about it yet, but I think we mentioned it. Yeah, exactly. It's called registered 0 because its contents are always 0. The contents are hardwired to 0. So you'll always have a 0 in register 0. Okay, so that's why it's special. Okay, so that's an example of a pseudo instruction that's still a single instruction, but it has a special value. But then there's another pseudo instruction, LI, load immediate. Okay, that's one you used, right? You used that in software number 1, right? We used the load immediate to put the address of the switches into a register, right? So we could use it later on with the load instruction to get the contents of the register or the contents of the switches into a register. Well, if you read that description, it says that the load immediate instruction is a pseudo instruction equivalent to the following instruction, add I, which is add immediate, where in that instruction, again, the 0 register is part of it. Okay, so it's like a special value that's within that instruction. But then it continues on that the load I is equal to that single add I instruction if the immediate value can be represented with 12 bits. If it can't be represented with 12 bits, then the LI instruction is a combination of 2 instructions, the add I along with LUI, which stands for load upper immediate. Okay, and you'll learn what load upper immediate is later on. But I just want to point out again, that's why the descriptions, right, that descriptive part of the instructions is so valuable, right? Because if you really want to understand what an instruction does, you look at that description. It gives you all you ever wanted to know about that instruction. Okay? All right, but the 6 real branch instructions are the following. Branch if equal, branch if not equal, branch if less than, branch if less than unsigned, branch if greater than or equal to, branch if greater than or equal to unsigned. Okay, so the only difference between BLT, every time I say that, I get hungry, right? But the only difference between BLT and BLTU, here the values are treated as signed, here unsigned, and same thing with the greater than or equal to. The only difference here is one treats the values as signed, the other is unsigned. Question.
Why would we use a real instruction over a pseudo instruction?
Well, it's usually the other way around, that in certain cases you may want to use a pseudo instruction because it's just more readable. But again, as far as the processor is concerned, it's the real instructions that get executed. And see, sometimes having that knowledge, especially that a pseudo instruction could be like multiple real instructions, comes into play when you're trying to figure out, what's going on with the hardware sometimes.
Was one of the modules on here to code the pseudo instructions and the individual instructions?
Oh, that's a good question. About that. Well, what actually gets processed by the Otter are the real instructions. Now, what we're eventually going to get to is that those control modules that we kind of talked a little bit about very superficially, and we're going to go in much more detail in about a month or so, but those control units, that FSM in the decoder and the control unit, that's the hardware that directs the rest of the hardware in the Otter to actually execute the instruction. So, as I pointed out in a previous class, if you look at the output of the control decoder, the outputs of the control decoder are select inputs to the muxes. And as you know, the muxes take from multiple inputs, one of those multiple inputs to the output. So you see the control unit decoder is using the muxes to kind of direct how the data is flowing through the rest of the processor. And then the FSM of the controller, most of the outputs there are read enables and write enables. So the FSM is controlling, at what times data gets read and at what times data gets written. So those two things together is what makes the instruction happen through the other component. And you'll see when you get to the point where you actually build those control units, what you did in hardware number 1. Okay, hardware number 1, that's when you reverse engineered the machine code, right? Like you looked at the machine code and then you came up with what the assembly instruction is. Well, when you model that control unit, you're writing the code that basically did what you did manually, right? Because think about what you did manually in that assignment. You looked at that machine code and, there's like, if you count the pseudo instructions, there's probably like 60 instructions, right? I think there's only about 30 real instructions, but, including pseudo instructions, there's probably double what the real instructions are. So do you remember what you did first to get, those 60 or so instructions down to a smaller number? Like, what was the first thing you looked at? Right, exactly. The opcode gave you what type of instruction it was, right? R type or I type. And each type was maybe, well, I think there's like maybe 12 instructions that are R type and maybe like, I don't know, maybe 18 instructions that are I type. Then there's only like 3 instructions that are S type and maybe, well, there's 6 instructions that are B type because those are the branch instructions. But you see the opcode narrowed the possibility of instructions down to a smaller amount. And then once you had the type of instruction, how did you narrow it down to the actual instruction? Because the opcode gave you the type, but then once you had the type, how did you get it to a single instruction? You had to look at other bits, right? You had to look at, there was 3 bits called the function bits, right? And that got you to the instruction. And then once you knew what the instruction was, you could see whether it depended on a register or it depended on like an immediate value. But you see what you did manually for that assignment, you're gonna end up writing code for the controllers that basically did that. Okay, so I know that was a long-winded answer to your question, but it was a very good question, so. But, you know, again, you know, as we go along, we're gonna get more detail, okay? All right, so when you look at these 6 real branch instructions, you'll notice that there's no branch if less than or equal to, and there's no branch if greater than. And, you know, the reason why there's no branch less than or equal to is because if we wanted to do something like this, use a branch with a less than or equal to. Now, what the X5 and the X6 represent here is that the X5 represents the contents of register 5. Okay, and X6 represents the contents of register 6. Okay, well, since we don't have a branch of less than or equal to, we can't do this, but what we could do is we could do the contents of register 6 greater than or equal to the contents of register 5. Okay, because we do have a branch of greater than or equal to. Okay, so that's why they don't have these, because it essentially be redundant, because you can do it with other branch instructions.
It says there's no branch is greater than, I'm looking at the sheet here, and it says that, BGT is branch is greater than, so.
Where are you looking?
On the board, it's saying there's no branch instruction, but there's something left, or do something. Or if you no branches, if there's, something greater than other.
What are you looking at? What instruction?
Actually, on the board, are you saying there's no left or equal instruction? Is that the only instruction it's missing? Okay, this is where it is.
I'm saying there's not these 2 instructions, branch if less than or equal to, or branch if greater than.
Some real instructions rather than pseudo instructions?
Any, if you go through there, none of them are that, right?
Is there a branch of
Oh, there is?
Yeah, there's a branch of greater than.
What is it? What's the? Okay, well, that's my mistake then.
Up there, above the property. Above the, what state is.
Branch if greater than. Okay, that's a mistake, sorry. But there's no branch if less than or equal to, right?
Yeah, the only.
Okay. Okay, so I guess it's talking about real instructions then. My mistake. Okay, so this is true if we're talking about real instructions, but there are pseudo instructions that do it. My mistake. Now, are those pseudo instructions multiple real instructions? Let's look. ELE. No, it doesn't look like it. It still looks like it's one. It still looks like it's one real instruction just with a special value for BLE. And then what was the other one? BGT. Okay. All right. I was thinking maybe if maybe if these were multiple instructions, then it would be better to use these here because these are single, but that's not the case either. So that was my mistake. I apologize for that. So we could do it either way. I mean, if the pseudo instructions were more than one instruction, there would be an efficiency reason to use the real instruction, right? So that doesn't look like it's the case. So anyway, thank you for pointing that out. You guys are a lot smarter than my earlier sections. They missed that. Okay. All right. But let's move on now. Okay, so let's move on. I've got several examples here to show how to do the branching in assembly. And then, like I said, we're going to get to the assignment, and I'll do the first part of the assignment, and then you're gonna do the second part. So, let's start here, because anytime, right, you're gonna write some assembly code, you always start out with a flow chart. Right, so you see, I have a flow chart, for this situation here. Now, back on the first day of class, we did talk about some flow chart symbols. All right, we have a circle for where you start and where you end. Do you remember, let's see, do you remember what this symbol is for? This one is a rectangle.
Process.
Yeah, just some sort of process, right? So if you're doing a mathematical process, if you're doing a logical process, whatever it may be, we use a rectangle. How about the parallelogram? Right, the rectangle with the slanted sides, what's that for? Right, that's for input output, right? So either you're reading input or you're writing to output, we use this symbol here. Okay, so those I think were the only symbols that we learned earlier. Well, when there's a decision to be made, whether you're gonna branch or not, we use a diamond shape. Okay, so here, what this symbol represents is making the decision as to whether the contents of register 5 are less than the contents of register 6. Okay, so if this is true, you know, we're gonna do some code over here. And if it's not true, we're gonna do some code here. Okay, so, you know, that's what the branch is talking about, right? If it's true, we're branching. If it's not true, we're just following through. So how you would do this flow chart in assembly is we would start with a branch if less than instruction. And then what this instruction is doing is comparing the contents of these two registers. It's seeing whether or not the contents of X5 is less than the contents of register X6. And if that's true, it's going to go to this piece of code here. If it's false, it's just going to go to the next instruction. Now notice I put a label here, right? I put a false label. That false label is optional. Okay, it's going to fall through whether that label, that false label is there or not. But it's good to have it just for readability. Okay, just to tell a person looking at, okay, it's going to go to this instruction if it's not true.
What are the diamonds used for in a flow chart?
When a decision is being made. So if you've got a diamond shape in your flow chart, that means you're going to have a branch instruction, right? Because that's what decides, you know, which path you're going to go. Okay. 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 The next thing is, notice that if it's not true and it does this code, right, where the false label is, notice that when it's done with that code, it jumps to the end here, right? This J is it's a jump instruction. Why do I need that? Because what would happen if I didn't have that jump right there? What would happen? Right, exactly. After it was done with the false code, it would start running the code for the true. Okay, which definitely we don't want. So once we're done with the false, right, we want to jump over the true code. Okay. Now, the other thing is when you look at the detailed description of our instructions in the assembler manual, you'll see that this is listed as IMM, which is short for immediate. And what's immediate again in assembly language? What's immediate? A value. Now, this came up, let's see, this came up also in hardware number 1, right? That in hardware number 1, when you were doing that reverse engineering, remember there was a JAL instruction, which is another type of jump instruction. And I talked about how in RARs, you can't put a number here. Okay, if you put a number here, RARs is going to come back with an error. Okay, RARs requires a label. Okay, where that label represents a number. But what I want to do next is I want to show you how to come up with what this number is. Okay, even though you're not going to put it into RARs. And the main reason I want to show you how to come up with this number is because it ties into the hardware. Okay, so each one of these instructions is at an address, right? Because remember the program counter, right, that you started building last time and maybe you finished and maybe you haven't, you still got to work on it today. But that program counter, that's the hardware that's providing the address of the instruction to be executed. And then our instructions in the code segment of our real memory, how are those instructions separated in address? Like I have an address or I have an instruction at address 0, then the next instruction is 4, then 8, right? And then 12, remember, because remember in the hardware again, you got your program counter, right? The register. Then there's that +4, right? That's connected between the output, one of the inputs to the mux. Right, the output of the mux goes to the in of the PC counter. So this is your, we call this PC out. Right here is your PC out +4. Right, then it had other inputs. One of them was a branch. One of the inputs, the other inputs, the mux is the branch. Then you had your select here. Right, the select went to PT source. Right, a PT source, that's one of the outputs of the control unit decoder. Okay, so each one of these instructions has an address. So I'm just making up these numbers here, but let's say this BLT instruction, let's say its address is all zeros and then 1C. Okay, so what is 1C, right? Because this is text. What is 1C in base 10?
16 plus 12,
Which is
32, 38.
28.
Okay.
But you're right, it's 16 plus 12. Right, because this is the 16s column, this is the ones column. But show 1 there, sorry. And C is equal to 12. So 12 times 1 plus 16, 28. Okay, so that's the address of the BLT. Then we're going to have some code. And let's say for this false code here, let's say there's 4 real instructions. So what would the address of the first real instruction be? What would it be in base 10? 32. 32, right? Because they're separated by 4. So what's 32 in hex? 20. Right? Because 2 times 16 is 32. Okay, so that's one of these 4 instructions. What's the second of the 4 instructions going to be at? What address? 24, right? Which is equal to 36 in base 10. That's 2 instructions. Okay, the third instruction of the false code. What address? 28, which is 40 in base 10. That's 3 instructions. Okay, and then the address of the 4th instruction of this 32 in hex, right? Or no, not 32 in hex. What would it be in hex? 2C. Which is 44 in base 10, right? That's the 4th instruction. Okay, so that takes care of these 4 real instructions. Then this jump is going to have an address. I'm just going to write the last 4. Right, what's 30? Right, which is 48 to the base 10. So, here I'm just, it's all zeros and then dash 0030. That's the address of this jump instruction. And then the instruction where the true label is, right? The first of this code here for the true code, this is going to be at what address? 34 in hex, which is 52 in base 10. So you see that's where this instruction is going to be. So you see this this number for the branch instruction, it's an offset. It's the difference of where the branch instruction is and where the label is. So you see the difference of this address 52, or well, 52 in base 10, which is 34 hex, and this address 1C where the branch instruction is. So you see this difference, 24, right? 52 minus 28. That's what the immediate number would be. Okay, because it's basically jumping 6 instructions.
So, complete true, you would put, 24.
Well, that's the number that the label represents. But like I said earlier, and like we said back during hardware number 1, when you did that assignment in RARS, right, the software we use to test the program, you can't put that immediate as a number. You have to use a label. If you put a number, RARS isn't going to like it. Okay.
So it's gonna read that, it's gonna read that label, and then it's gonna read the second label, but to generate the number that corresponds to it.
Right, yeah, the software is figuring it out, exactly. But like I told some people individually, back when you were doing that assignment, I don't think I told the class. Even though RARS requires a label, like you can't put the number there, even if RARS did accept the number, you would still want to use the label, right? Because it's more readable. And also, it's more convenient because if you use numbers and then you have to go in there and start editing, like adding instructions or subtracting instructions, well, then you're going to have to go in there and change all the numbers to make sure they still line up. But by using labels, the software does that for you. When you do edits, the software, recalculates what those numbers have to be. Okay, but here's the reason why I wanted to go over this, is because going to the hardware, right? Remember what you're working on, or maybe you finished this, right? The program counter, right? Last meeting's assignment. One of the inputs to the MUX is called branch. And if you were to look at the Otter diagram, right? That diagram, I didn't put a diagram on the bench today, but hopefully you have one of those diagrams, or you can grab it on the computer. Well, this branch input to the MUX, it goes to another piece of hardware that's called the branch address generator. And you're gonna design that, you're gonna model that, I think in a couple of weeks, a few more classes from now. And what this branch address generator does is that it takes the present address, the present instruction address, and adds the offset to it. So, in this case here, coming out of this branch address generator would be, the 1C plus the 24. So the PC source, which goes to the control unit, if it's 0, right? If the PC source is equal to 0, well, then the next instruction is going to get executed, right? Because if PC source is 0, this input that has the current instruction address plus 4 would get connected to our PC register, right? But if it's a branch instruction, the PC source is going to be whatever this input is, which I think is 2 on this MUX, and it will allow through to the PC counter the present address plus the offset. So that's what gets it to jump to branch. Okay, and it's the same kind of deal with the jump instruction, because one of these other inputs to the MUX is a jump. Okay, and the jump instruction works the same way. Okay, it has an immediate value that's an offset to the present instruction address. Okay, so the reason I wanted to spend time and go through this, again, is to show how the software and the hardware are intermingled. Right? You can't really understand why the hardware is the way it is unless you understand the instruction set. You can't really understand why the instruction set is the way it is unless you understand the hardware. They go hand in hand. Okay? Okay, so let's do a few more examples here, and then we'll take a break. Here, we're looking at this flow chart, where now we're comparing the contents of a register to a number.
Wait, sorry, I just wanted to ask that blue code, like, is that,
Let's
like,
see, blue code. What do you-
sorry,
what do you-
like the colon and like the stuff before that? -0030?
Oh, this, well,
that
this is
Actual,
an address.
okay, so is that actually included as code? Or
No, the code is what's in black here. This blue I wrote, that's the address where this instruction is at.
Okay.
So this instruction, is at 1C. And then, see, that's what we were figuring out here, because I said there was 4 real instructions in between VLC and this end. So, this is the address of the VLT. Then the first real instruction of the false code is at this address, then the second one, third one, fourth one. And then this jump is at this address, right? Because each instruction has an address, right? Because it's in that part of our memory called the code segment. And all the instructions are separated by 4 an address, because again, each instruction is 32 bits and memory is byte addressable. So that's why it's by 4.
Okay.
Yeah, question?
And just to clarify, is that a colon or a J? Or-
This is J for jump.
Okay.
Yeah, these are J's for jump.
So I was thinking about this, and it's almost like at the end of an if statement, it just knows to go to the end of the thing. That's kind of what we're doing here. Like in the more abstract programming language or in Vivado, like at the end of the if, it'll like know to go to the end, but here we have to tell it because otherwise it'll run
Right.
one by one by one.
Correct. Yeah. It's like when you look at a high level instruction, whatever language it is, that high level instruction is made out of multiple assembly language instructions. And and that assembly language program made out of those instructions, are what goes to the machine code, which are the bits. And sometimes there's a one-to-one, like we said, like, a single assembly language is a single real instruction, right? Single machine code, but other times it's multiple. Yeah, and I guess I forgot to point out here, although I talked about it during hardware 1, that one way to end a program is just having it to jump back to itself. So you see here, this is just going to keep jumping to the same line. I mean, when you end a program like this, it's called a trap. Now, sometimes you don't need this, but sometimes, like in the assignment you're going to be working on, the way you end the program is by outputting some data, right? So when you're finished with the program, it's because it's taking whatever data you processed and, sending it out to LEDs or sending it out to, 7 segments or something like that.
So instead of JN, we put relevant instruction to tend to something else.
Well, yeah, you'll see when I get to the example, you'll see, because you actually, you did that in software number 1, because software number 1, if you go back and look, the last instruction was just, we were storing the half word to LEDs, right? We're sending it to an address that, where the LEDs were at. Okay. Yeah. Okay, but let's get back to this. Once I'm done with these two, we'll take a 5-minute break and then we'll go over that example. But here, see the difference between this flow chart and the one we just looked at is here we're comparing 2 register contents, right? Contents of register 5 to contents of register 6. Here, we're comparing contents of a register to just a number. And this is 10, okay, base 10, it's not 1, 0 binary, it's 10, okay? So what the assembly code would look like is you would start with this add I command. Okay, this stands for add immediate. So what it does is it takes the immediate value that you put here, it adds it to this register, and then it puts the result in this register, which I have as register 6. Now, what's the contents of register 0 again? We said earlier, register 0, because that's the 0 register. So see, it's just adding 10 to 0 and then putting that in register 6. So after this instruction is executed, register 6 has 10 in it. Okay, now we're going to compare the contents of register 5 to the contents of register 6, which is now 10. And we're going to see whether it's equal or not. So this is a branch if equal. Okay, so if they're equal, we're going to do this true code. If they're not equal, we'll do this false code. And in both cases, once we're done, we go to the end. Again, we have this jump here, so we don't do the true code after the false code. Okay, so the main reason I wanted to show you this was just how to compare a content of a register to just like a number as opposed to contents of another register. Do you have a question?
Yeah, you don't really need to define false, right? Because
Yeah, this is optional. That's correct. This label is optional, but it's a good idea to put it there just because it's more readable. Especially when you get more specific labels, which I'll show when we get to the example, but you are right, you don't have to have it. The program would run the same with or without it.
So does this not, I'm a little confused, for the BEQ line where it says true, does it not just go immediately to the false line?
No, because it's gonna execute this instruction before here, because as long as the program doesn't branch or jump, it just goes in order. So, this instruction is for an address before this one. So since this isn't a branch or a jump, it goes here. So now it evaluates this before it goes any further. Like if this is false, it will fall through to the next instruction address. But if it's true, it's gonna take this immediate as an offset and add it to this instruction to get to here. Okay?
So do you have to do false before true? Like, is that always the order? You said false is like a label, right? Because it's optional.
Right, again, it doesn't even have to be, well, you can call this whatever you want. You don't have to call it true. You could call it, Ralph if you want to. It's just gonna go wherever that label is.
Do you even need a jump end after the end statement? Because I feel like you already have it's already gonna jump there. Right? Why do you need a J end there?
Here?
No, on the bottom one.
Well, this is just a way to end. I mean, like I said earlier, this could be just outputting the data to some output device. Like it might not be there. But I'm just saying this is sometimes how a program is. The only reason I'm showing this is because there's this thing called a trap. And I just wanted to make sure you knew what a trap was. Right, it's called a trap just because once it gets here, it keeps just jumping to itself.
So like that's if you want to stop the program and like keep it in suspense, sort of.
Yeah. Yeah, exactly. I mean, I think in most cases, you're gonna output whatever you process, right? So you probably won't run into this, but again, I just wanted to have it there as just a learning item.
So I know this is kind of a snippet, but you in this case, you look at, it's not initialize X5 to be anything. If you look at that in Mars, would X5 be uploading, like, or would it be set to something else?
Well, if you're doing this in RARs, remember in RARs, you can step through the program. So just like in the first software assignment, remember we had like reading from the switches 3 times in a row. So in RARs, you could put the data for the first read of the switches. And then before you went to the next read, you could change the data, right? And then, yeah, so it's the same thing here. It's just, when you get to this point in RARs, you can just put a value for the register. But you're right, in the real case, you'd probably initialize that to something. Okay, last one before we take a little break is this one here, and this basically represents a case statement. Okay, so we have a decision here where we're comparing the contents of register 5 to the number 5. If that's true, we're going to do this. If not, we're then going to compare. Whoops, question. Oh, turn the camera. Thank you. I always forget. Thank you for reminding me. Thank you. Okay. So yeah, you do a comparison of the contents of register 5 to a 5. True, you're going to do this stuff. If not, you're now going to make a comparison of that same register contents to 10. Do this. If not, compare it to 15. Do this. If not, then you're just going to do some whatever kind of stuff that none of that is true. Okay. So it's basically a case statement, right? Because a case statement, you have like multiple options depending on a variable value. Okay, well, this is what the assembly would look like. Again, you have an add I where here we're adding 5 to 0, putting that result of 5 into register 6. Then we're doing the comparison. If it's equal, we're going to jump down and do this code. If not, we're going to add 5 to register 6, which is still 5. So the result will be 10. Do that comparison. If it's true, right, they'll do this code. If not, it just drops down to this next add I, add another 5. We'll end up with the result of 15. Do the comparison. If it's true, do this code. And then, let's see, where are we at? Oh, and then if none of it's true, right, we just have some default code. Again, this is optional here, this label, but you know, again, it would be a good thing to have, because if anything else, it kind of relates to the case statement we talked about, right? Because the case statement has a default option. Okay, and it just ends the same way.
Can you explain what LBL?
Oh, LBL is just, you know, my shorthand for label, but again, I could have called this Ralph, Mary, and Suzanne. You know, or, you know, emu, cheetah, and meerkat. You know, you can name these labels anything. Because the software will know it by a number, right? The software is just going to assign that offset to whatever you put there as a label. All right, so let's take a 5-minute break to about 1/4 and then I'll go over the first part, or we'll go over the first part of software number 2 as a class. And then again, you'll do the second part of it. Okay? So come back at 1/4 and I'll continue on.
Here, that's a couple of questions. So is register 0, is that always gonna be?
Right, yeah, we're gonna make it that way. That's one of the things actually, next week when you do the reg file, that's where that happens, like. You're gonna model it, right, in Verilog, and yeah, you're gonna make it where that register always has content of 0.
It's like,
No, I wouldn't have laughed about this.
If we look at the instruction, right, if you look at the manual.
Started working.
BLT branch plus N. See, it's BLT, then source register, registers, immediate. And like we've been saying now, in Raj, you always put a little, right, I'll take a number. But I just wanted to show you how you would figure out the number because it relates to the hardware. Right. And you see the way we come up with 24 is that this BLT instruction is at this address. This is its instruction address. And where the true label is at this address. So it takes the difference. This number is the difference of this address and this one. So the hardware, the way it actually makes this happen is it takes the address that this branch instruction is at, and it will add 24 to it to get it to go to this address. And the piece of hardware that does it is this thing called a branch address generator that you're gonna model, not next week, I think it's the week after. Okay. But you'll see when we get there, it has inputs coming into it, like it has the address of the current instruction. And it has another input that's gonna have this offset. And what you're gonna model and what this does is it takes that current address and it adds the offset to it. And then that's one of the inputs to this mux. And the mux is being controlled by this PC source that's coming from the controller. And you'll see when you design that controller, you're gonna be writing code that does what you did manually, when you were reverse engineering it, and that's what's gonna have the PC source choose the branch input that now is gonna have the current address plus the offset, and that's what the next instruction address is gonna be. So you see, that's how the hardware and the software work together.
okay. Could you explain one last time what you mean by real pseudo instruction? Like, is that, I first thought about like pseudocode, but I don't think that's.
Yeah, again, if you look at the description, see, all these will tell you whether it's pseudocode or not. Like, if it doesn't say pseudocode, it's a real instruction. So you see BLT is a real instruction. But you see like BLTZ, branch if less than, or branch if less than 0. See, it goes that BLTZ instruction is a pseudo instruction based on the BLT instruction. It's equivalent to BLT, source register 1x0. So you see what's different is.
So it's like a modification of the original one.
Yeah, it has some special value, or like the load immediate. See, this load immediate, it's also a pseudo instruction. Now, it can be one real instruction if if the immediate is a 12-bit immediate, but if your immediate is more than 12 bits, then it's two real instructions. It's add I also with this LUI.
Okay.
So where that's important to know is if your pseudo instruction is made out of multiple real instructions, well, it's gonna take longer to actually execute it, right? It's gonna be 32 instructions.
So pseudo instruction would be less efficient than if you just did 2 lines of real instructions. So is it right?
Well, efficiency is determined by how many real instructions you have, because that's what's actually executed. So yeah, if you can do something in one real instruction as opposed to, pseudo instruction that has multiple real instructions, then it would be more efficient.
Okay, so it just comes down to like how can you represent it, I guess, like in.
Right, yeah, there's, like any coding, right, there's multiple ways to do the same thing. So in assembly language, the less real instructions you use, the less time it will take to execute that code.
Branch and greater.
Now, in this class, we're not gonna grade you,
Division.
so you don't have to be.
So who's the time, so just time.
Right.
Mhm.
Well, that's the question, is it shifted binary, is it shifted text? Hey, Gary.
Actually, let me start here, and then I can answer either during the class or after we go through this example. Yeah.
Have we started yet, or? still-
Well, let me go through this, and then if you have questions, I can answer after this example. I just want to get through this example so people can start the assignment. Okay, so let's, let's look at the board here, because this will help you do the assignment that you have to do for software number 2. So this is part 1. Okay, we're gonna read a 32-bit unsigned value from the switches. Okay, you have the switch address here that you saw in the first software assignment. And if that switch data is greater than or equal to this number, this is a base 10 number, we're gonna take the switch data and divide by 4. And it says to ignore the remainder. Okay, if the value is less than this amount, well, then we're gonna multiply the switch data by 2. And in both cases, we're gonna write the result to the 7-segment display. So before you write any assembly code, what do we draw first? Flow chart, exactly. So remember, in a flow chart, we have this simple start. And then what are we gonna do next? Read read the switch, right? You gotta read the switch data. So what kind of symbol is that when you're reading input data? Yeah, the parallelogram. Right, so this is gonna be read switches. Okay, so once we get that switch data, we're gonna compare it to this number and based on whether it's greater than or equal to or not. That's gonna decide what we're gonna do, right? If it's greater than or equal to, we're gonna divide by 4. If it's not, we're gonna multiply by 2. So what do you think comes next? What symbol do you think comes next? The diamond shape, right? Because we gotta make a decision here, right? Are you gonna branch or not branch, depending on how the switch data compares to that number, right? 32,768. So in your flow chart, put a diamond shape. Right, and then you can just put something like in greater than or equal to 32,768. Right, if it's true, we're gonna do something. And if it's false, we're gonna do something else. Now, well, I'll show you later on. But I'll just do it right now. Okay, so how do we show when we're gonna do some process? What symbol? Yeah, the square or rectangle. Right, so here, if it's greater than or equal to this number, we're gonna divide by 4. And here, if it's not greater than or equal to 32,768, we're gonna divide by 2. Okay, and then in either case, whether we divide by 4 or divide by 2, we're going to show the result on a 7-segment display. So you see these two would now come together. Right? So 502 divided by 4, we're then gonna output it to a 7-second slide. So what symbol do I use when I output something? Or a logogram. Right, so output 7 seconds. And then you just go to put that in ends or stops. Okay, so any questions on the flow chart? What questions? We get up to the end of the response to the response to the response. Oh, well, see right here, it stands to ignore the remaining. But yeah, I just worry about the motion. Yeah, make it. No, I just need switch data here. We're reading the data from the switches, that's what we're comparing to that number, so. But you can put switch data. You know, it's clear. Yeah. All right, so ready for the assembly code. All right, well, you did this in software number 1. In software number 1, you read from switches. And you remember how you did that? What was the first instruction in order to read from the switches? Load up. There was something before that. That was actually the second instruction. Load immediate. What were we loading when we did that load immediate? Like the address of the switch. Yeah, because see the reason we gotta do the load immediate first is because then the load, whether it's a half word or word or byte, it needs an address in order to get the contents into a register from that address. Okay, so yeah, you start with the load immediate. Load immediate, leave register, I chose register 5. Then we're going to put this address of the switches into register 5. So your immediate value is going to be the address. Now again, I use an underscore for readability, but in Arch you don't put an underscore, you just put all the rows. But this is going to put the address of the switches into this register. Okay, then when you did software number 1, we were interested in 16 bits, that switch data. So that's why we use the half word, right? The load half word. Load half word unsigned, I think. I think we were treating it as unsigned. Okay, but here, it's not 16 bits, it's 32 bits. So what are we going to use? What load? Load word. Yeah, if you go look at the instruction set again, it is a LW for load word. Okay, so load word, and I'm going to use register 6. And the load word, just like the load half word, it has an offset. And then in parentheses, you put the register. So what this instruction is going to do, it's going to be 0, add it to the contents of register 5, this address on the switches, and then take the contents of that address and put it in the register 6. So you see, it takes these 2 instructions to put the switch data into a register. The register here is register 6. Out of curiosity, why wouldn't you want to load a word on the X file again? Register 5 again. Oh, here, yeah. Well, you'll see because later on when we go to output this, it's good to still have this address in 5. So it's just so I can keep this address in 5. Because if I put 5 here, it's going to overwrite that address with the data. That address, right? And just because later on I'm going to output stuff, I still want to have this address. It just makes things easier. And you'll see why. Okay. Now, here's something to know. When you look at the instructions, there's an LV load byte. There's an LVU load byte unsigned. There's an LH load half word. There's a load HU load half word unsigned. There's LW the load word, but there's no LWU. There's no load word unsigned. slide.
Like anything more than they can do that.
You've got it, yeah, and again, if you look at the detailed description of the instructions, you'll see that LV load byte says that, it's sign extended. Right, so that means it's taking and making certain steps and sign extended. LVU is zero extended, same thing as adding a zero. And same thing with LH and LH2, so both, LH is sign extended, if LH2 is added with zero. LW is already 32 bits, so we don't have to extend it. So that's why I know LW. Okay, so anyway, let's continue on now. So we have the contents of the switches in our register 6. Now, to make this comparison, we gotta put this number into the register. Right? Because if you do any comparison with the branch instructions, it's comparing the contents of two registers. Right, so I gotta put this 32,768 into the register. So we can use another load kit. And I use register 7. Okay, so this is gonna put the 32,768 into this register 7. And in RAR, if you just put the number here, it defaults to base 10, so it's gonna take this as a base 10. But we want a base 16, you gotta put 0x. Oh yeah. But you know, you just write it as a number. If you want it to be exact. Good question. I don't know if I've ever tried a binary because you're doing the 32 bits or 60 bits typically. It's easier to do in the past. I don't know, you can try it. I'm not sure what you probably have to put some symbol. I don't know. Okay, so now we'll do the comparison. So to do the comparison, I've got a branch greater than or equal to unsigned, since we're treating it as unsigned. And it's two registers that we're comparing with the contents of the two registers, right? The switch data is X is comparing it with the number here. So if this is true, I want a branch to do division, right? Because if it's true, we're going to divide by 4. So this is where being descriptive can be more readable. Like instead of using true or label, I use UID4. Okay. And, you know, that's going to be a little later on because this is not true. Well, then we're going to multiply by 2. And so if this isn't true, we're not in the range. We're going to go to the next instruction. Multiply. So I'm going to put a multiply label. Multiply 2 label, but again, that's optional. But again, it's good for me to know, right? Someone that doesn't know what you're doing, then it's not familiar with what you're doing, to say, oh, this is some multiplication. Okay, so we're going to multiply our switch data by 2. So what's an easy way to multiply binary by a whole number power of 2? Shift the bits. Okay. So multiply by 2, what do I use that? Switch together. Which direction do you want to shift? Right, I'm going to shift by how many places? 1 place. Right, so 1 place to the left and bring in a 0. We're going to multiply by 2. So let's see if we have an instruction how to do that. Okay, so I'm looking at my instruction assembler language manual. And look, it's a FLL that stands for logical shift left. And when I look at this instruction, it has a destination register and 2 source registers. And the description tells me that this instruction left shifts the data in the source register RS1 by the number of times specified in source register RS2, replaces the data by 0, which is what we want, then stores the result in destination register RS2. Okay, so this instruction requires 3 registers, 2 source registers in the destination. Okay, let's look at SLLI. That's logical shift left and right. Okay, notice that This has a destination register, a source register, and then a number that the call shift amount, which is the same as in the mean, it's just a number. And this tells us that this instruction left shift the data in the source register RS1 by the number of times specified by the immediate, on the 5-bit shift amount value. Places the 18 by 0, which stores the result in destination register RE. So you could use either one of those instructions, but if you use the SLL, you're going to have to put how much you want to ship by in a register first. So you would have to do like an add I. But if I use the SLLI, I don't need to put the number into a register first because it's right there in the instruction. Or maybe something like that. That's a good question. I mean, that's the only thing I can think of, and maybe something else, but. Not for shifting, because it wouldn't make any sense, because if you want to do it the other way, it's just shift right. But sometimes it needs to be like, for example, here in the branch instructions, if you were branching to an earlier instruction in the program, then this mean it would be negative. Okay, so means the branches can be negative, but you want to run into a negative here for the shift. All right, so anyway, what I would write here is I would write SLLI for shift left logic immediate. And I have X6, and 1. Basically, what this is going to do is shift the contents of register 6 where our switch gate is one place to the left, and replace the indicated bits with 0, and then put the results in register 6. Okay. Then I would put a JN before I put the code for divide, right? Because I don't want to divide, right? Once I end multiplying, I would jump to the end. Okay, but if the bridge was true, right, this condition was true, that would be the next thing I would have this label. And I want to divide by 4. Okay, so what's an easy way to do division by a whole number power of 2? Shift right. I want to divide by 4. How many places to write? Good. So let's look at our instruction set to see if we can do that. All right. Well, I'm looking at my instruction set here. And let's see, I get to, look at here, there's an arithmetic shift right. There's an arithmetic shift right immediate. Oh, but then also there's a logical shift right and a logical shift right immediate. Now, the logical shift right and the logical shift right immediate, it's the same idea as what we talked about, the shift left. One of them, you have to put whatever you want to shift by in a register first, and the other one, you already got the immediate. And the logical shift is what we want to do when we do multiple division by powers of 2. Does anyone know what's meant by arithmetic shift right or arithmetic shift right immediate? How that compares to a logical shift right? So what we want to do is a logical shift. Anyone know what the difference is with arithmetic shift right and logical shift right? I wouldn't expect anyone unless somewhere else you heard about it, because we didn't talk about it, and it's not talked about in 133, I don't think. Okay, what the difference is, when you do a logical shift, you're replacing the dedicated bits with 0, right? Which is what we want when we're multiplying or dividing by a whole number power 2. Arithmetic logical shift, the vacated bits get replaced with the most significant bit. All right, so if your most significant bit is a 1, so basically bits are going to be replaced with 1s instead of 0. The most significant bit is 0, it's going to replace the vacated bit with 0. Now, where this comes into play, where you use it, is with sign numbers. Okay, because the arithmetic shift would maintain the sign bit. Is it simple for bits? You must get convinced before or after the shift? Before. Yeah, whatever it is before, because if it's signed, right, that is the sign bit. Right, so you maintain it. use that and listen to it. Okay, so. We want to do a shift right. Logic, immediate. And same thing. With the registers. It's gonna take the switch data. Shift right 2 places and then put the results in X6. Then I would just want to end this. I was talking about earlier where, you know, if you're gonna output data, right, you're not gonna have a trap. It's your last instruction of your assembly code. You're just gonna be outputting this data, this result. They need it for the result, find having a result in register 6. Now we want to take the contents of register 6 and write it out to our 7 segments, right, at this address. So what type of instruction do we use when we want to write data? We use load to read, we use what to write? Store, right? So it's going to be a store word. Store word. And contents of register 6, and that's the content where our answer is. Okay, and now here again an example of why we have this offset in both the load and also the store pins. Because now what it can do, because this address of the solutions is still in register 5, like we talked about earlier, right? The reason I did this not X, because now I'm going to look at that result. The 7 second display that's in an hour that's 40 tests. Switch address. So all I have to do is add 40 tests to what's already registered 5. Yeah, 7 segment address. So that's what I would do here. They put text 40 and then register 5. So this is going to add 40 tests what's already in register 5. This address is switches. And the contents of register 6 is going to go to this address. Okay, the 7 segment. Instead of the serial instruction, you're going to add I apply the SW. The 0 is 40 and 5 in that SW. Is that taken as serial instruction? Well, let's look. That's why we have this detailed description here. So let's find SW. I'm not sure. Yeah, we can't find SW. I guess they don't have the stored in alphabetical order. It goes from all the logic. Oh, here it is. Yeah, that's weird. I thought all the instructions were alphabetical, but SW is not in alphabetical order. The SW doesn't look like it's a pseudo commune. It's a real instruction. And so, like when in doubt, just look at the instruction. Okay, so we should be able to make part 2. Okay, so just like what I did in part 1, for part 2, start with a flow chart. And once you have a flow chart, you go ahead and start working on these things. So like I said earlier, if you haven't completed the program counter, do that first, because that's due tomorrow. And then this software number 2, part 2, that's due Monday of next week. Same. J and over here. J and well, there. No, it's very. The only reason I added these is just to show you what trap means for something like that. But more often, you're probably. The difference between this here, you're with context or it's to another. See, so this is very different context, right? You're at one context, other. Here. The number of things. Per minute. Yeah. Yeah. So yeah, that, I guess there's reasons to show this after one, or that we'll talk about it. The other one is this, that will, when you use add I to this, zero register. Okay, so that's in your, oh, I don't write it out. Okay, that's- True. Again, it's example, they're the same. Here's what I might have. I don't know where it's true from. Whenever you have a question about it, it's we modified it, I didn't sign off there. The number we actually need. The value of our, you know, the Leland and value ours. You know, it's comparing. Yeah, and they're going to be greater. So, yeah, it's the reason why the instructions like this. See that in the software. Hardware makes that branch actually start. In fact, it takes the current instruction address and adds this number. And then it's up to program counter or check once it's out. Next program instruction Yeah, well, yeah, let's look at the construction. It's. So, you know, the first registered destination. Destination, but it's always a new concept. Ours one is the source, register, and then you have your meter. There's another, so you read the description of it, so basically, that's the on. We have software longer. Yeah, I think it was the first one was just. But he's actually doing it. This was just how you determine what will happen. This is how it was done. And you never played it. You're talking about. Now,
And it was just on.
Yeah, but that's back to the media. You could, but it's gotta be more efficient. Actually, you know what, never mind.